Hello everyone, I'm Xiaodongqi from School of Data Science and Engineering, East China Normal University. It's a great honor to attend ICD 2020 and share our work, BFT-Store storage partition for permissioned blockchain via Erasure Coding with you. I'm going to introduce our work from the following 5 parts: motivation, preliminaries, solution, experiment, and conclusion. And let's start from the motivation. Blockchain is a distributed append-only ledger maintained by all nodes in an untrustworthy environment. In general, each node holds a complete copy of block data, and a consensus protocol such as PBFT ensures the data consistency among whole network. Thus, the overall storage contribution per block is O(n), where n is the number of nodes. However, with this full replication manner, each node has to devote huge storage space to preserving blocks. For example, the Ethereum network generates about 0.2 gigabyte data every day. Particularly, in a permissioned blockchain with higher transaction throughput, blocks are produced at a fast speed. To address this, some techniques are introduced. The lightweight client just saves block headers rather than enter blockchain. However, this technique will just reduce the overhead of client while the full node still reserves a complete copy of blockchain. The basic idea of Lightning Network is to restrain the volume of block data by reducing on-chain data. Although this approach eases the stress of storage for each node, it does not subvert the full replication mechanism fundamentally. In this work, we break the full replication of blockchain by combining PBFT and Erasure Coding. We then give some preliminaries about the PBFT and Erasure Coding. Out of the n nodes, at most f are malicious such that n is greater than or equal to 3f plus 1, which can misbehave in arbitrary way, and the remaining participants are honest. PBFT is a 3-phases protocol, including pre-prepare, prepare, and commit. In pre-prepare phase, the leader proposes a block to all nodes. Subsequently, in prepare phase, each node votes for the proposed block if it is correct by broadcasting signed vote message. Upon receiving n-f votes with correct signatures for the proposed block, everyone broadcasts its vote for the block again in commit phase. Finally, a node commits the block once receiving more than n-f votes again. Erasure coding provides significantly lower storage overhead than multi-replication manner at the same fault tolerance level. Reed-Solomon coding, the most widely used erasure coding. Given a set of k data blocks, encodes them into n chunks with m parities, donated by KMRS. Both the original block and the parity are termed as chunk in this work. The coding is done such that any k out of n chunks are sufficient to reconstruct the original data, which can tolerate the absence of m chunks. There are 3 main challenges to partition block data over nodes in blockchain system. First, how to guarantee all nodes never become lost in Byzantine environment, even 40 nodes tamper data or keep silent. Second, how to support flexible scalability. New nodes added to blockchain. With more participants, the enter storage capability of system is increased, which means that more block data can be stored by system. Last, how to enhance read performance on encoded partitions distributed over nodes. Compared with full replication manner, the read performance of blockchain declines due to the data exchange among nodes for decoding. It is feasible to devise an EC-based storage partitioning for blockchain system. We can encode every n-f blocks into n chunks with f parities. Then the n chunks are distributed over n nodes. Thereby, at least n-f chunks are stored on honest nodes, which are sufficient to reconstruct the original blocks. In this way, the storage consumption per block is reduced from On to O1. However, in PBFT setting, it is impossible to ensure On-F honest nodes have resolved the correct chunks, because the agreement of a block is reached for a node when it receives N-F commit votes from others. It only promises that at least N-2F honest nodes will commit the block due to the existence of F40 nodes. In addition, there is no trusted third party to encode blocks and dispatch chunks. Besides, Erasure coding cannot verify the correctness of chunks, thus we need to design a mechanism to verify chunks. BFT-Store encodes every N-2F original blocks into N chunks with 2F parities, and each node preserves a unique chunk. The process to encode every N-2F blocks is called a coding round. In a coding round, chunks are donated by C0, C1 until Cn-1. According to the assumption of PBFT, at least N-2F chunks are stored on honest nodes, and all blocks can be recovered based on these chunks by Erasure decoding. Since there is no centralized node in PBFT, each node encodes blocks independently without any information exchange. After encoding, each node stores a unique chunk and deletes the rest. Besides, hash values of the N chunks are stored by all nodes for verification. In order to achieve this, all nodes are sorted by their public keys, and the position in this list is treated as the global index for each node. In this way, the sorted node list is identical among all honest nodes because everyone knows others' public keys. In a coding round, each node calculates a permutation tau for 0 to N-1 based on the hash value of N-2F blocks. Since blocks are agreed by major nodes, honest nodes will gain the same permutation. Then node Ni stores the chunk C tau I and deletes others. At this time, we say node Ni is the target node of chunk C tau I. BFT-Store is a storage engine for blockchain with Byzantine fault tolerance. Each client sends transactions to blockchain system. The transactions are packaged as blocks for consensus among the nodes and are then returned into BFT-Store for persistence. Clients read blocks by sending requests to nodes in BFT-Store. To read a block B, a client sends its request to one node Ni in BFT-Store. Node Ni faces different cases when reads block B. First, if node Ni is the target node of block B, Ni can read it locally and sends B to client directly. Second, if Ni is not the target node of block B, it tries to pull B from its target node. If the target node is honest, it transmits B back to Ni. Third, if the target node is faulty and keeps silent or sends incorrect block, node Ni is forced to recover all blocks by Erasure decoding. To achieve this, Ni broadcasts requests to all nodes, and other nodes respond with their chunks. Upon collecting N-2F correct chunks, Ni recovers all blocks in a coding round via Erasure decoding and picks B from them as a replay to client. However, the reading performance is poor since about one-third requests will incur decoding to recover blocks, which causes massive data transmissions and heavy CPU calculation. To overcome this problem, we replicate each chunk over C different nodes. Hence, a block has C different target nodes, then block B is recovered by decoding only if all its target nodes are faulty. Thereby, the probability of decoding is decreased exponentially as C increases. For example, in the figure, when N is 6 and K is equal to 3, the block 1 is replicated on nodes N0, N4, and N5. Besides, Each node sets a LRU cache to buffer blocks read from others to reduce network transmission. With the addition of nodes, the schema of RS coding needs to be updated and historical blocks should be re-encoded. Since all blocks are partitioned over network, none stores a full copy of blockchain. Thereby, node cannot encode blocks independently. In addition, it is difficult for a node to judge whether the progresses of re-encoding on others are accomplished. This may result in unexpected loss of blocks during re-encoding. For instance, node Ni deletes block B when it finishes re-encoding, but other nodes have not synchronized B from Ni. Subsequently, block B becomes unavailable and cannot be recovered forever. BFT-Store arranges a node as the leader to coordinate the process of re-encoding, and the others are backups. With addition of new nodes, the number of all and faulty nodes becomes N' and F' respectively. The re-encoding is deployed round by round. There are 4 phases for re-encoding blocks in a coding round. First, the leader broadcasts a decode message to all the nodes to request chunks of a round. Second, each backup responds to leader with its chunks. Third, the leader recovers all original blocks based on N-2F different chunks received from backups. Then it broadcasts a re-encode message including the blocks. Last, when backup receives a re-encode message from the leader, it re-encodes blocks into N' chunks and stores its own chunks. Then, backup sends a coding finished message to leader indicating the accomplishment of re-encoding for current round. Upon collecting N' minus F' coding finished messages, the leader starts to re-encoding blocks of next coding round. We implement BFT-Store in Tendermint, an open-source platform adopts PBFT protocol for consensus. At the network layer, each node maintains a TCP connection with its peers so that all nodes can communicate with each other via P2P protocol. All experiments are conducted upon a cluster of 4 machines. To test the scalability, we run multiple Tendermint instances on each machine to simulate a middle-sized network with up to 20 nodes. We employ a full replication manner as the baseline method and study the situation where the block size is fixed to 1 megabyte. Specifically, we introduced a new parameter R to restrict the number of faulty nodes in system. In particular, the number of all nodes is greater than or equal to Rf plus 1, such that R is greater than or equal to 3. A greater R means fewer faulty nodes in system and more storage space can be saved. Figure A reports the average storage consumption per block under different cases against the number of nodes. In our novel manner, the storage consumption per block increases very slightly when more nodes join. For example, when R is 4 and C equals 3. For example, when R is 4 and C equals 3, the storage consumption per block is 5 MB, even there are 20 nodes. Figure B shows the overall storage capability of the blockchain system under different mechanisms. Assuming each node only owns 200 MB storage space, the overall storage capability keeps merely 200 blocks for replication manner, while that of BFT-Store increases significantly as the network grows. Figure C reports the latency for block read. For replication manner, the latency for block access keeps about 0.076 milliseconds due to no data transmission between 2 nodes. In comparison, the latency increases significantly in our manner as more nodes join system because the volume of data transmitted for decoding increases. When n is 20 and r equals 4, the latency for block access even reaches 5.2 milliseconds. Figure D reports the latency of request when r is 5, which C rises from 1 to 3. As expected, with more replicates for each chunk, the latency of block read decreases because fewer decoding is deployed. The latency of block read decreases because fewer decoding is deployed. In this work, we combine PBFT and Erasure Coding to partition blocks over all nodes in blockchain system. Specifically, we exploit Erasure Coding for blockchain to reduce storage complexity per block from ON to O1. Propose a hybrid Erasure Coding and Multi-Replication to improve reading performance over encoded partitions. Design a re-encoding approach to deal with addition of new nodes. Thank you.